Okay, let me see. How do I change my slides? Okay, good. So I would like to start with the inspiration. It seems like we are in a very important point of our project when we are questioning what it is PITHIA NRF in spirit. So my contribution to that discussion would be as follows. I would like to answer 3 questions. Why new data providers would come to us? What would be so attractive that they say, oh, we would like to register our data collections? Not only because we are part of the original project, but in future. Also, why would fellow scientists and students would use our eScience Center for the research? And especially that FAIR concept, findable, accessible, interoperable, and reusable. What does it mean for us? And I will talk about 2 aspects of it, our metadata and data being findable and interoperable. Then we will go to the question of the mechanics of it. So I will start with brief definitions of schema, ontology, and resources. I think there is still a little bit of confusion going on. What do they mean? What do we mean by ontology, for example? And then lessons learned so far, because I've seen a fair share of the different registrations. They're all very interesting. And I will just go through some simpler examples and a little bit more complicated ones. We'll talk about the critical part of the registration. It's not important to register individual organizations and projects. It's all about, for the instrument data, for measurements data, is to being able to correctly register platforms and instruments, and then acquisition and computation part of it and the process. So with this, here's my contribution to the spirit of the PITHIA NRF. Why would data provider would come to us? And I thought about it by just thinking about me as the data provider, and the argument that my data collections will become fair is a very strong one. It will be findable. Someone can find my data by using the search engine, and whereas previously without this registration, that data would not be findable. So that's a good one. It will be provided with DOI, which means that my data will be persistent and repeatable. The results of investigation will be repeatable. And that is an extremely strong argument for our work to register data correctly using FAIR principles. Repeatability is very important. And also, just this week, there is a publication about threat from the artificial intelligence people that the latest softwares, such as the ChatPGM, which is a famous one, they can write scientific papers now. And there were like a board of reviewers looking at these scientific papers, trying to identify whether they were written by robots or the humans. And actually, the identification not that good. There are false positive and false negatives. As much as 30% of the robot-written papers were considered to be written by humans. So in that case, the ability of using the DOIs to get to the real data and make it repeatable is a strong argument, will become even stronger with time. Finally, the PITHIA, for me, as a data provider, also is offering a persistent storage solution. It's not that large, but I don't need that large because it's relative to a small number of publications. There's a subset of data. I thought it was a strong argument for me. eScience Center will operate and distribute models. So that is also a great thing. Because as I mentioned before, sometimes model becomes so popular that they can really suffer from the too much request of computations. And the eScience Center, if it can run certain models in its environment, I thought it was a very strong point. Usage analytics may be helpful as well. what I mean by usage analytics is like who is using my data? That would be interesting to know. You know, sometimes our Amazon directors are asking, do you know, by the way, there's a Digizon in Wuhan, who is really looking at our data? That is type of usage analytics that may be helpful. That's why, as a data provider, I would be interested in joining the PITHIA consortium and using the data registration process to do it. Next question is, why would scientists come to us? I would say that the search, select, discover new knowledge is a strong thing, and that's what virtual observatories are all about. We are not there yet, because in order to really ensure that we get a very good metadata about nice collections that can be searched and combined together to produce and discover new knowledge, we need more than this small number of data providers that we have today. We need a more comprehensive storage, coverage of all the resources out there. That comes only with time. We need more time so that more people would join us. And then ideally, that would be 100% perfect if the comprehensive coverage of all resources. There would be all anagrams, for example, ever made, things like that. Then the scientists would come to us because we can run models. The more models, the better. A very interesting point I learned this week, which I didn't know before, and it's one of the disruptive points at this point in our project, is those smart data analytics tools that can be applied to our data. That I wasn't aware that that was one of the strong considerations. How can we attract scientists to come to us? Because if we offer various smarts how to analyze the data, that would be we need, of course, to carefully research that in future, because it is a challenging task. Okay, so that's in spirit. So search, selection, and discovery aspects. I see two aspects of this capability of our engine. One of them is search by content, and that's what we are doing. The red section of this slide is what I am personally consider myself responsible for. So that would be possible to search data collections if we know what we are looking for in terms of the feature of interest and observed properties, computation and instrument types, things like that. So we will be able to find everything like interferometers and things like that. The other one is search data availability by context. It was mentioned two days ago, I believe, or 3 days ago, that we should be providing our scientists a capability of searching by coincidence, meaning that our users should be able to ask a question: can we find data by something special in terms of elevated heliogeospace activity? If that activity exceeds some particular threshold, we should be able to ask PITHIA, can you find something in your collections for this particular period of time? That was mentioned before. I'm familiar with this type of search by context, meaning that do you have something during this Hunga Tonga event, for example, or this DST going below -100. So we will be able to search by activity. I think it's not that uncommon. It's actually this doesn't have to be arranged by PITHIA providers. There's standard capabilities we could research. I'm sure there's at least one which we used for the virtual wave observatory back in the days. You just dial in the threshold numbers and it brings back the particular intervals of time when these thresholds are exceeded. And that's all we need, right? After that, we should be able to find our collections. There's a problem, though. As you remember, as a part of simplifying our schema, our design of PITHIA data, PITHIA metadata, right, we decided that we do not record data availability for our observational resources. Some models can be run for any time, right? You just dial in time period of interest and the model runs and hash the answer. But the observational resources may have a coverage or not, and we do not store this capability. And the answer, which was very nicely and gracefully provided by Tamas right away, is that solution is that we will provide a new type of interaction with the data collection. We should be able to query our data provider for the data availability. I think that is one way of providing this search by context. I think it's going to be very important that we do that. There is also search by conjunction, which is a stronger search of data availability when you are matching not only time, but also location. So you would ask, is there a conjunction of two spacecraft sitting on the same magnetic field line, for example? Or is there a coverage when the overhead radio occultation instrument matches within a certain radius of ground observatory for comparison, right? Ground ionizing observatory or ground incoherent scatter radar observatory. Similarly, there's a problem. We do not record spacecraft ephemeris today. So these orbit propagators, we do not have these algorithms. We didn't commit to that. But there is certainly, again, I've seen these things happening. There are already solutions where the external resources could be involved somehow to do the orbit propagators. So this is how we attract more users so that they would come to us and say, oh, by the way, did you see that PITHIA? You just dial in whatever instrument you would like to have a conjunction with, and then it gives you the answers. That would work nicely. Let's continue on our path. 12 steps, whose idea was that? You see that FAIR principle is not a walk in the park. It's a requirement of our data and metadata to be standard. It is a very strong requirement, and we are not going to be. It's not going to be easy for us to really solve it. Not easy. So we were starting that work back in the days, almost 10 years ago. So the ISO observations and measurements was selected as a standard for our metadata. At that time, it was very generic. It was produced by, I think, geography community, by essentially geologists for their observations and measurements. So we spent a few years on to really work to extend it to space physics. We added ontology of space physics, like standard terminology. And we had to customize that ISO schema, extend it in order to cover what specific differences are when we are using spacecrafts and various other variables. It's really, our domain is quite significantly different from geography. So in 2020, we selected that in agreement with everyone. We selected that ISO ESPAS work as a prototype for PITHIA. First, we simplified it in 10 steps in 2021. There was a remarkable effort to review it and add more functionality, which we ended up with 12 steps as a result of that work. So 12 steps is on our current design. So let's talk about definitions. Schema. Schema is a standard for naming and organizing metadata. So when we are talking about 12 steps for data collections and 3 steps for catalogs, so these elements that we need to do, catalog, or computation, acquisition, instrument, platform. These are all schema. So there's an organization of our metadata in different elements. Back in the days, we used the term data model. But I think if we start using that data model today, it's going to generate so much confusion because we have models, we have data already. So my suggestion is to use the word schema. So the schema is really the way we organize our metadata. Ontology is a standard vocabulary. Yeah, what terminology we use for space physics domain. So here's a quick check for you. So observed property is schema. F2 layer picked electron density is ontology. Okay, so that's the way how you distinguish between schema and ontology. Resources are those XML files that everyone is preparing. Those are resources. We register our data by producing the resource XML files. So quickly, just think about it. I will not call anyone to answer this right away, but think about it. So data registration, we are talking about data registration now. Data registration is adding new information to what? Schema, yes, no, or maybe. Resources, yes, no, maybe. Or ontology, yes, no, maybe. So think about it briefly, and here's the answer. We are not going to change schema. 12 steps and 3 steps are there for a long time. We have frozen that development. We are not going to be doing new schema designs. Then next one, resources. Oh yes, that's going to be a big one. So that is the XML files that everyone will be providing as the new data registration are appearing. So the question is, what is the answer for ontology? And the answer is maybe. The reason is that we didn't see certain things previously. As we keep registering data from various data providers, there's once in a while we need to add new observables, new observed properties. Sometimes new dimensionality comes in. So new computational type, some model that we, model algorithm that we think deserves its own category in the ontology. So that dictionary will be expanded. I know I promised that we will be talking about what kind of extension to ontology was already accomplished during those years of PITHIA, but in the interest of time, I suggest we do not talk about it today. Maybe sometime later I will do it's kind of a specialized topic, what kind of new things the PITHIA-NRF project resulted in terms of new ontology contributions. Okay, 12 steps of registration, you've seen all that. So I draw your attention to the bright orange stars there. 2 of them say OP, which is observed property, and 1 of them on the top and the right stands a feature of interest. That's where our searchable by content information is stored. So when you're looking for a particular data collection by its content, so these items are present in number 7, number 9, and number 12. The rest is also important, but in a different way. Everything in the gray color, you've seen the 12 steps already many times. We will not discuss today. So we'll briefly talk about platform instrument, and we'll spend most time talking about 7, 8, 9, and 10, very briefly about 12 and 11 and 12. So let's start with platform and instrument. So the platform is just a place where something happens. So usually it's an observatory, whether it's on the ground or in the space, an instrument and something that senses, interacts with Mother Nature to collect information. So let's take an example. There's a whisper instrument on cluster that we just registered relatively early in our project. If you look at the left part, I'm not sure if you see my pointer, but probably it doesn't help that much. So if you look at the left part, here's 4 spacecraft that contribute cluster. Excuse me. So that registration will require 5 platform documents and 1 instrument document. Okay, it's not 4 instrument documents and 4 platform documents. It's 5 and 1. Why 5? Because the platforms, each of the 4 spacecraft will be registered as the platform. Salsa, Samba, Rumba, Tango, that's 4. And then there will be 1 combined platform document called platform cluster, which inside you will see child platform link, which will point to those 4 documents for the individual satellites. Okay, so there's 5 of them. And the instrument will be just 1 document, not 4. And it will be a whisper instrument, and its particular instrument type is it's an in situ relaxation sound. Okay. Any questions on this? Why is the 5 and 1? No questions, no answers. Let me go on with this. Are you still there, by the way? Talking to the, cannot hear you at all. Okay.
We are still here.
And
we are awake.
I'm so glad, because I thought I was like talking for the last 20 minutes to a lost internet connection. All right, so anyway, let's continue on our path. All right, we just registered platform and instrument, okay? So the next step is acquisition capability. So when you look on the left, that's the instrument that we already registered. Inside of that whisper instrument, apparently it works in 2 different operational modes. One of them is active, the other one is passive. And correspondingly in acquisition capabilities, we will have 2 different acquisition capabilities. One of them is called active spectrogram. The other one is passive spectrogram. The difference is whether the transmitter is sending pulses or not, or it's a pure listen-only experiment. So each of those documents, that everything in green here, that active spectrogram is not a vocabulary term, it's not ontology. It's a particular name. It's a particular name that was introduced by the data provider, not the standard ontology. Active spectrogram. So if you look inside, there is inside that active spectrogram document, you will see a portion of it called capabilities. And inside of that capabilities, you will find the observed property. That is the findable part of our design. So in that particular case, the observed property itself is electromagnetic wave electric field and a very specific property of electric field called voltage spectral density. By the way, if Fabian is in the audience, I think we need to review that because I think we picked the observed property incorrectly. It has to be voltage spectral density. I noticed that by looking at the units. If you look at the units, they are in the volt per root hertz. That is a spectral density. And it's in voltage, not power, it's voltage. And it's also in the log scale. But log scale is not important, but it's the correctly identify what exactly you are observing. So that's the correct name for the observed properties. It's the electric field of the electromagnetic wave because it's electric antenna. So it picks up the electric field of the wave. And then there is a bandwidth of the receiver involved. That's why it's voltage spectrum density. The dimensionality instance at each, it's a regular sampling. So you're collecting one-dimensional spectrum in terms of its frequency. That's just understood. If you look at the time, as the time progresses, that makes this data product, it makes it a spectrogram. There is particular cadence, and a couple of qualifiers will distinguish active spectrogram from passive spectrogram. So these are acquisition capabilities that the instrument has. So we just combine now them into acquisition documents. So acquisition describes the whole experiment. Somewhere we need to indicate that there are 4 whisper instruments, relaxation sounders, not just one, and that is done inside the acquisition document. Any questions on that? Acquisition combines platforms and instruments. So in that little diagram on the bottom right, you see that we combine the instrument with the platform. And it's done by these capability links. So each link combines the 1, 2, 3, 4 different platforms with the corresponding active spectrogram acquisition capabilities. And if you look inside active spectrogram, right, active spectrogram says that instrument mode, it explains, yes, active spectrogram uses whisper in its active mode. Okay? That's the acquisition part. Now, what else is there? There are a little bit of computation because, yes, you can already find the spectrograms from the whisper instrument on cluster.
Ivan, there is a question from the room.
Sorry, Ivan, it's Fabien speaking. I just wanted to add that there is only one whisper instrument file because all whisper instruments are identical on 4 spacecraft. If there would be a difference between the 4 instruments, there should be 4 files for instruments.
Absolutely.
Yeah,
You're
so
right.
I just wanted to precise that because maybe it was not clear. It's because the instrument is exactly the same on the 4 satellites. So that's why we have only one instrument XML file.
Absolutely, you are absolutely correct, Fabian. This is not the case for some other data collections. For example, the ionizon networks. We have all sorts of different ionizon models, right? And not only that, not only they are different, so we need to produce acquisition capabilities for every ionizon model, right? But also each platform has a history of different instruments, right? Do you remember that discussion in the past? Yeah, so we decided that we would like to keep history on each observatory, at what time which instrument model was operating. Yeah, that is now possible. It was not possible before. Now with the 12-step procedure, it is possible. Okay, here, indeed, all instruments are identical enough, so that's why this is relatively simple. We just combine in this particular example, just the active spectrograms combines links from the acquisition capabilities in the active spectrogram with 1, 2, 3, 4, with the 4 different platforms. That is required for different platforms because their location is different. Yeah, that's why there are 4 of them. Okay, let's continue with this. Whisper. So computation capabilities. It appears to be that there are some computations are required in order to derive what is called I would call it actionable data, meaning something that we can plug into different models, because the spectrogram is a nice display full of interesting features and etc. But our models require plasma density. It has to be extracted from the spectrogram image. Very similar to the CCDR instrument, the Doppler radar. They are recording the spectrograms as well, but there is a computational part of it where from the image of the spectrogram, the knowledge of the, in this case, in case of the whisper instrument, the knowledge of the electron plasma frequency is extracted. That is the computation step. So in order to record that, we introduce 2 computation capability documents. On the left is a spectrogram selection. Apparently, there are passive, active, and combined spectrograms, and just select one of them which looks best. And on the right, that's the extraction algorithm that from the spectrogram extracts the resonance frequency electron plasma That's the observed property in kilohertz. And that's going to be a dimensionality instance 1D points. Why is it plural points? Because there are 4 sounders flown in the constellation, right? That's why it's not just one. It's very specific to cluster. Many other relaxation sounders, they just would have 1D point because there's only one location. Correspondingly, if you're looking at the dimensionality timeline, the 2D time series is stacked. That's because we will have a multiple panel, 4 panels with the variability of the electron plasma frequency. Now, why this dimensionality is so important? Because there is a strong call that we start producing a particular smart analytics tools to work with our data, and those tools will apply to particular data character. So there will be some tools for the time series, some tools for the images, maybe specific tools for spectrograms. So this is the way we would be able to differentiate. Think about it as a Photoshop, right? So this is a Photoshop of things. So we would create a Photoshop with the various filters, labels that you can add, and things like that, and stretching and I don't know, filtering. So these all sections have to be applicable to the data, input data in very specific standard format. Maybe just more than one, yes, that's okay. So the formats can be different, but certainly the dimensionality has to be precise. There will be a set of tools for spectrograms and a set of tools for time series. So 2 computation capabilities. Then we actually have to write down how the whole acquisition works, because there are 4 cluster platforms. We have to register that these computation capabilities apply. They are identical again, but they apply to our 4 platforms. So 2 computation documents. And now on the left is process, and the right is data collection. That is step 11 and 12. That's the end of the data registration for Whisper. So the process is just a list of things that are required to do, starting from scratch, starting from the beginning of the measurement. Oh, I'm sorry. From the beginning of the measurements. That process has the active spectrogram is collected, passive collected. Then the spectrogram selection works to find the best of the options. And then the computation of electron plasma frequency is done from spectrogram, because spectrogram it's a frequency, right? And then the final computation is that the plasma density is computed from the electron plasma frequency. Okay? On the right, the data collection, the final step, I apologize again, the final step of data registration. Data collection, if you look inside that document, it says the procedure is this one. So that's what we do. That is searchable, right? The acquisition capabilities, computation capabilities will be findable. And collection results will point to the resource. There's a Whisper landing page. So that's URL is provided here, the data collections. And then there will be linked to a project cluster. Data level will be explained that it's a level 2 derived information, because we are doing the electron plasma frequency from spectrogram. Data quality flag is this, quality flag is that. So this is it. I am getting very close to the end of the this presentation. Let me quickly go through an example of model registration, DTM 2020, atmospheric model from Sean. So the computation capabilities, there are no instrument involved. So they can do neutral density and neutral temperature. So there are 2 computation capabilities. There are 5 different observed properties, because there's a possibility of evaluating neutral density combined, but also for O2 and helium. So there are 5 of these. The same for neutral temperature. So there will be 2 computation capability documents. And in order to combine them in the computation, we just say the computation of neutral density uses 1 computation capability, right? Easy. There's no question of platform or anything anymore. Just say my computation is doing that. And the other computation temperatures, neutral temperature is doing the neutral temperature computation capabilities. And then the end, the process is just we first compute neutral density, then we compute neutral temperature. That's it. That's the process. And data collection on the right, procedure points to that document, so 1 process document. Data level 4, because we think that this empirical model has been validated by many publications. To level 4, we assigned it validated. Data quality is DQ4, which is the highest, I think, quality. Again, because we believe the data, this model has the highest possible quality, is a validated data. There are some metadata quality flags that I don't cite here. License, contact information. That's it. That's the example of data registration for the thermosphere. How am I doing in time? I probably lost. I'm speaking for about 35 minutes.
Yeah,
now, right?
we changed the agenda a little bit, but I think there was. Originally, your talk was planned for 30 minutes. No, your talk was planned for 45 minutes. So you can still go for 10 minutes.
Okay, I'm wrapping up. I'm just going here and there, looking at what people do. So let me just, I have just 3 or 4 maybe last slides very quickly, because it's, I see what other contributors are doing, the CCDR, the Doppler radar. Curiously, they have to implement the double-nested platform definitions, because at the level 1, all individual platforms, say in South Africa, there are multiple transmitters, 1 receiver site. These are all different geographic locations. Of course, there are not 5 of them. It's just a schematic. In Belgium, I'm sure there are not 5 of them, maybe a different number. In Czechia and Argentina, maybe I missed other locations. Sorry, Slovakia, probably 1 more. But the idea is you have to first create platform document for every single location of these parts. Then the level 2, for each radar installation, you build 1 document with the child platforms pointing to 1, 2, 3, 4, 5. Okay, so that would be a level 2. And then for the whole network of the CCDR in various parts of the planet, that would be a level 3 platform document, which will have a child platform elements pointing to radar installation platform documents. Very curious design, yeah. Double nested. Other notable submissions, ISCAT is the first data collections where begin and end times are used in linking platforms and instruments, platforms and acquisition capabilities. Apparently, there are certain remote stations were part of the Incoherent Cadre from 1981 to 2012. So to indicate that this capability existed only for a limited number of years. So that's the capability link that we were talking about. It combines platform, is the platform ISCAT mainland, with acquisition capabilities, which is like this remote UHF thing. And that's the time span. It says it started in this time, ended in that time. So if we ever decide that we would like to keep history of how ionozones will operate in each particular observatories, that's the way we will do. Because the platform will be the same, right? It's the same observatory, say in Durg, but the acquisition capabilities will be different depending on which instrument operated. There will be a Digizon 256, or maybe if you have a good history recollection going back into your 1950s, I'm not sure, Tobias, correct me if I'm wrong. So if you have...
You are correct.
Okay. Yeah, so That's the way you do it. You would have multiple capability links with time span options saying when they started working and when they ended work. So that would be the way to do it with the ionozones. So that's ISCAD. GIM, or GIM, I'm not sure what's the correct way. It's global, so G seems like it's not global, so maybe it's GIM. So, so global ionospheric maps from GNSS, that's the contribution from our UPC rapid network team. They really went out to specify all the computations that they do. And that is a very long it's not like 2 steps, it's a 9-step operation when every step produces no observable properties. Very curious, yeah. So that's quite a design. Okay, that's all I have. So probably there's some time left for questions.
Yeah. So, are there questions or comments on this? None? I have maybe one question myself, which is that, as you mentioned, for the models, they have no instruments or so associated to them. That's of course true for instance, IRI, but if you then use an assimilative model like the real-time IRI, would the relationship to the data that is being assimilated, is that documented?
Yes. Yeah. Yes.
So then you would have a model that does need to be associated with instruments as well.
Right, but it's not associated in terms of like specifying which instrument is there, right? But it is associated. Let's take a simpler example first, right? IRI, well, it's not a simulative model, but it has something which is called an input parameter. Because you need, in order to run IRI, you need to know sunspot number, right? And you need coefficients for the IGRF model. And now I'm learning that you also need F10.7. So, and for the storm option, you need KP. So all these things that a model needs in order to operate need to be cited, right? We need to list them. That there is a provision in the schema that for the models, we specify exactly what they need in order to run. Now, a simulative model, there are a couple of moments. First of all, a simulative model needs to cite that, yes, in order for it to run, you need let's see. So you have to specify for IRTEM, for example, right, that there is a need to run ionizant measurements as an input, and the way we do it, we in the link we specify which are the inputs. We are pointing to a data collection.
Right, but so my fundamental question is, if, for instance, you want to register the IRTAM, can you do that before all the ionosons that are included are registered themselves? Because if an ionoson is not yet as an instrument registered, then you cannot link to it yet. Because that platform or that data acquisition capability is not yet registered itself. So
it's a great question, Tobias. Yeah.
Because that would make registering something like IRTAM, if you want to register all the contributing instruments first, then it would be a huge work.
The way I remember it, we do not enforce that the data collection, if this is a data collection somewhere, we do not enforce that it is registered already. which is a simplification exactly, that's just you mentioned. Because there will be models like Euphoria, for example, has a couple of stages. It runs first stage, then the second stage, and each stage is also a complicated mix of different models running one after the other. So that chain of the computation, I think we will be able to define a sequence of computations, right? But also, I think there will be two data collections that one will be stating that it requires as input a different data collection. But that link, I believe, and David will correct me, and I will review and get back to you, Tobias, on that. But that link is not enforced.
Okay.
Regarding this link, is the stations that are contributing with this data for an assimilative model are always the same? Because, for instance, IRTAM, I understand that gets data from any station that operates. It can get from 50 stations or 40 stations, depending on how many stations operate. So what is the point of specifying which stations provide data to the model?
Right. It's not done in terms of instrument. That was a question from Tobias. Do we need to specify which instruments are contributing?
So if the answer is no, that makes it a lot easier to register real-time assimilative models, because if the answer would be yes, then that would be a very complicated process.
I think that it is we have to specify the type of instruments contributing to the model,
but not the individual.
The locations of the instruments, because it may be from any location.
Yeah.
Right.
So only
actually,
the instrument.
You made a very important new point now, indeed. You said that the type of instrument used for assimilation needs to be stated. This is very important because, for example, I am looking for, say, F0, F2, right? Measurements. But a simulative model is as good as a measurement very often. And the way the system will also offer IRTM it should offer, let me check on that. It should also offer the IRTM as a question, where do I find the peak density of the ionosphere? Because IRTM document has a one link to the instrument type which states ionozone. You're right, Anna. That's the way it is done.